Welcome to this explainer. Okay, picture this. You're exploring this gorgeous, sprawling digital world, getting totally lost in the game, and then, boom. You notice this weird, shifting line of shadows on the ground just a few feet in front of you. Today, we're totally demystifying this super distracting visual anomaly. We're going to uncover the exact engineering behind it, and more importantly, look at how cloud computing might actually be the ultimate cure.
You know, this shared grievance is just perfectly captured in a Reddit thread we found. One user pointed out that Grand Theft Auto 5 is a major offender here. And another added, I got about 50 hours into Metal Gear Solid 5 before I saw it there too, and now I can't unsee it. And man, they hit the nail on the head, right? That is the absolute curse of this visual quirk. Once you actually notice this harsh line where shadow qualities aggressively shift, your brain absolutely locks onto it. It becomes this massive, distracting break in immersion when you're just trying to lose yourself in an open world. So it naturally begs the question, is this just a glitch, or is it actually by design? I mean, you drop hundreds, maybe thousands of dollars on high-end gaming hardware, and seeing shadows suddenly snap into high-res as you walk forward, well, it feels like a glaring error. Are these jarring visual artifacts just sloppy coding from rushed studios? Or are we looking at a necessary engineering compromise forced on us by the physical limits of our graphics cards? All right, let's break down the symptoms first. All over the internet, gamers regularly report seeing this distinct visual bubble around their characters. In massive titles like Fallout 4, it shows up as a hard line right where the rendering transition happens. Over in The Witcher 3, players report weird checkerboard patterns on the ground, or even low walls that look almost scrubbed clean of any depth. That is, until you get really close, and suddenly the detailed shadows pop in. Some people even try tweaking the game files to push this boundary further back, but the bubble is always there. It honestly feels like you're walking around with a spotlight of high-fidelity graphics, completely surrounded by a blurry, low-res world.
Well, here is the kicker. This isn't a bug at all. Nope. The real culprit is an intentional, highly documented NVIDIA rendering technique known as Cascaded shadow maps, or CSM for short. Now, shadow maps are a standard way to get realistic shadows. But in huge open environments, capturing everything in one single high-resolution map is just computationally impossible. So CSM was basically designed to fix those jagged, pixelated shadows, what we call aliasing. It does this by giving higher resolution depth textures to objects close to you and progressively lower resolution maps for stuff that's far away. NVIDIA actually mapped this out brilliantly in their engineering specs. Basically, the camera's vision, also called the view frustum, which is just that 3D pyramid shape showing exactly what your character sees, gets mathematically sliced into separate chunks based on distance. You've got a near light section and a far light section. By slicing up the view like this, nearby objects get detailed shadow maps so they look crisp, while distant objects just get coarse approximations. Because, let's be honest, your eyes aren't going to notice the lower quality way off in the distance anyway. So what's the actual math behind this magic? It involves three really specific rendering steps in the CSM algorithm. First up, the game engine renders the scene's depth from the light's perspective, like the sun up in the sky. Second, it renders the whole scene again from your camera's point of view. And finally, for literally every single pixel drawn on your screen, the engine checks its z-value, which is just its mathematical distance from the camera. It uses that precise distance to seamlessly select the correct shadow map resolution on the fly. It is a staggering amount of computation happening dozens of times every single second, just to keep the illusion alive. But you know, it gets even trickier when things are off-screen. If there is an object outside your view, let's say a really tall tree or a bird flying just past the camera, and it needs to cast a shadow into your vision, the engine has to draw these mathematically extended bounding boxes backwards. It basically renders the light's point of view far enough back to catch every single potential occluder. If the engine didn't do this, objects outside your immediate view just wouldn't cast shadows into the area you're currently looking at, which would completely break reality. And when we compare the final results side by side, the visual leap is practically night and day. With a basic one-split shadow map, the terrain looks blocky, jagged, and totally lacks fine detail. But if you jump to a much smoother 3-split map of that exact same scene, the shadows on the hills or around a character are way tighter and infinitely more realistic. This is exactly why devs rely on cascaded shadow maps. Splitting the view fundamentally improves the quality without needing some impossibly massive, single, ultra-high-res texture map.
But here's the problem. As modern games push absolutely massive polygon counts and crazy geometric complexity, developers find themselves in a constant tug of war. Shadows become exponentially more expensive to compute as these scenes get more detailed. So, to balance visual perfection with the hardware limits of video RAM or VRAM, developers often have to shrink those high-resolution shadow distances. They literally pull that high-quality near split closer and closer to the player just to save performance. And that, my friends, is exactly what creates that highly noticeable, super distracting visual bubble that drives us all crazy. So, how on earth do we actually fix it? Well, going back to that Reddit thread, one frustrated gamer put it perfectly. This is probably one of the biggest reasons why I cannot wait for true real-time ray tracing to take hold. No more fake, hack tricks to approximate how lighting really works. And they are absolutely right. The ultimate dream for gamers and developers is to just ditch these hacky visual approximation tricks, like cascaded shadow maps, entirely, and just use real physics instead. To understand why this fixes things, we really need to look at modern rendering. Standard rasterization, which includes those shadow maps we just talked about, is essentially a computationally cheaper illusion. It's just a poorer physical approximation of light. Ray tracing, on the other hand, actually models the true transport of light. It tracks individual light rays as they bounce and bend around a scene exactly like they do in the real world. The result? Perfect, realistic, soft shadows and ambient occlusion with absolutely zero pop-in. But it comes at a tremendous computational cost. Now, while modern high-end PC graphics cards can just brute force their way through ray tracing using hardware acceleration, we run into a massive roadblock as gaming goes portable. Think about the future of interactive experiences like the metaverse. It relies heavily on thin clients. Your mobile phones, standalone VR headsets, extended reality devices. These thin clients absolutely struggle to run ray tracing natively. They just cannot beat the physical constraints of heat generation and severe battery drain. Literally, if you tried to run full real-time ray tracing on a mobile XR headset today, it would overheat and drain its battery almost instantly. But researchers are working on a cutting-edge solution, and honestly, this is where the tech gets genuinely mind-blowing. It relies on 5G multi-access edge computing, or MEC. The idea here is to use cloud assistance to handle that heavy hybrid rendering, but instead of pinging a server hundreds of miles away and getting terrible input lag, 5G MEC brings the remote server, the edge node, just one or two network hops away from your device. This gives you the ultra-low latency and insane bandwidth needed to compute heavy ray tracing on the server and instantly beam those flawless results back to your mobile device. We're talking about authentic, lab-free lighting, powered entirely by the cloud. And this massive shift in global infrastructure leaves us with a pretty provocative final thought. If 5G edge computing can eventually render perfect, ray-traced lighting right from the cloud with zero latency and absolutely zero pop-in, well, will our expensive local graphics cards just become a ghost of the past? If your lightweight phone or XR headset can display physically accurate graphics beamed instantaneously from an edge node, the entire hardware landscape as we know it might change forever. Thanks for joining me on this explainer, and I hope you never look at a video game shadow the exact same way again.